Good afternoon. Good afternoon. My name is Christian Samper. I'm the director of the National Museum of Natural History, and I would like to welcome all of you here to the museum and to the Smithsonian Institution for this very interesting symposium we have for all of you this afternoon. Some of you in the audience know, but others not, that my own background is as a tropical biologist. And I also grew up in a tropical country in Colombia. And I used to be the deputy director at STRI at the Smithsonian Tropical Research Institute before I came to the museum. So it's right up my alley to come here and talk about tropical rainforests. The symposium today about will the rainforest survive, the new threats and realities of the tropical extinction crisis, will allow us to explore some of the questions and the science behind the consequences of tropical deforestation on biological diversity. As you know, there's been a tremendous amount of interest in rainforests for a number of years. Some of it stems from the science and from the extraordinary biological diversity that is found in tropical rainforests. For example, a single small 25-hectare plot in the rainforest of Yasuni in Ecuador that is part of the Center for Tropical Forest Science. In 25 hectares, you have more species of trees than in all of North America. And we've always wondered as biologists, what are the mechanisms that have been behind this biological diversity? How did it originate and how is it maintained? But in recent decades, as a result of the increasing pressures from human beings and populations in these areas, and the growing loss of some of the areas of tropical forests, there's also been great interest in the conservation of these areas. And behind all of this is a great interest to all of us in understanding how are the current and future changes affecting these tropical forests, and how are they going to affect the biological diversity and the cultural diversity found in these regions. In a recent study completed just 3 years ago, the Millennium Ecosystem Assessment, of which I was one of the members, we surveyed all of the terrestrial ecosystems of the globe, and we estimate that about 25% of all the terrestrial ecosystems of the world have been transformed in the last 200 years, directly as a result of human activities. Tropical rainforests are around there, about 25% historically by 1950, but in the last decade we've lost more than in the last 3 decades we've lost more than 5%, and the projections suggest that we may lose another 25% by the year 2050. On the other hand, a number of studies interested in looking at the extinction of species on this planet have been doing rigorous assessments and documenting some of these. For example, a recent study by the World Conservation Union, the IUCN, surveyed all 5,487 known species of mammals in the world, and although there are very few documented extinctions, about 76 species of mammals in total, about 25% of the known living species of mammals are considered to be in danger of extinction, most of these in tropical rainforest areas. And as we look into the future, we know that there are important changes happening and that will take place in this planet that will pose additional threats, whether it's the transformation of forest areas as a result of human pressures, the overexploitation of species that are important for timber, the impact of invasive species that are being moved around the world linked to globalization, the growing pollution tied in with some of the urban centers, and of course, climate change. And the fact is, we know that these rainforests have changed in the past and will change dramatically in the future in response to these drivers of change. So today we will be exploring some of these issues, and we've got a wonderful lineup of speakers that will tell us a little bit more about some of their work. We will first have a background and overview of the symposium by Bill Laurance, and we'll also have toward the end a summary and major conclusions by Joe Wright. Both of them are staff scientists at the Smithsonian Tropical Research Institute. And toward the end of the session, we will have a panel where you will all have a chance to pose questions or make comments about this issue. And we'll make sure at the end we ask all of our panelists to tell us a little bit more, not about their conclusions in general, but just as a heads up, I'm going to ask each of them to tell us what was the most interesting thing they learned today and that they're taking away from this symposium. Now, the Smithsonian has a long tradition of work related to tropical forest, as you will hear in just a moment from our secretary. We generate knowledge through research at places like the Smithsonian Tropical Research Institute. We document this diversity through the biological and cultural collections held at places like this museum, and we have the opportunity to share it with millions of visitors that come to our museums and use our websites. But in my view, the Smithsonian is also a place where we bring ideas together. It is a venue where we can come together to talk about important and relevant issues for society, like the future of rainforests, and be able to see how science can inform us as a society. And that's exactly what we're about to do today. I want to take a moment just to acknowledge a number of people that have worked making this possible. I want to acknowledge Ira Rubinoff, who's here with us in the audience, the longtime director of STRIDE, but also who had the idea to develop this symposium when he was the acting undersecretary for science here at the Smithsonian. Bill Laurance and Joe Wright, who I mentioned, who have been the co-chairs in the process leading up to the symposium today. And of course, all of the staff at STRIDE and the Office of the Undersecretary for Science, especially Mike Lang and Marguerite Butler, for all of their work in the organization of this, as well as members of the Smithsonian National Board that have supported this, including Peggy Burnett and Stephen Hoke, who are here with us somewhere. Where are you, Peggy? There you are, and Stephen. And of course, Frank Levinson as well, who's been a major supporter of the activities and the research at STRIDE. And now it is my pleasure to introduce to you our secretary, the 12th secretary of the Smithsonian Institution. Wayne Clough came to the Smithsonian in July of last year. He came to us having served as the president of Georgia Tech University for 14 years. He is an engineer by training and has had a very distinguished career. But I know that in the last 6 months that he's been here, he's enjoyed tremendously getting to know the scope and the diversity of activities that we do, but he also has shown tremendous interest for the research and the scholarship that happens here and highlighting the importance for society. So without further ado, Wayne Clough.
Thank you very, very much. Thank you, Christian, for that wonderful introduction. It is indeed my honor to represent the Smithsonian as its 12th secretary. And it has been a wonderful learning experience for the last 6 months. And I have a feeling after having done it for 6 months, it will never end. And that's one of the joys of this job. Christian, of course, was nice enough to introduce me, but he serves as director of this wonderful museum, one of the great science museums in the world. And he helped organize this symposium, and to him we say thank you. Let me also welcome our Smithsonian colleagues who are with us today, our distinguished global panel of participants. We have congressional staff here, agency staff, members of the press, and all of our special guests. Welcome to the Smithsonian and Bayard Auditorium. Christian recognized Peggy Burnett and Stephen Hope, members of our national board, and they not only have supported us morally and with their financial resources, but by the fact they are here, I can tell you they are as excited about this meeting as anybody here. And so we thank them, Peggy and Stephen, and all members of the board. Thank all of you for coming for what I believe will be a very lively and important meeting for the future. Biologist E.O. Wilson warned years ago, biological diversity is in trouble. Mass extinctions are commonplace, especially in tropical regions where most of the biological diversity occurs. The ongoing loss of biodiversity is the greatest since the end of the Mesozoic period, 65 million years ago. We are fortunate to have with us today many of the top experts in the world who, through their research, have the best insights on this extinction crisis. This is an important opportunity for all of them to inform the issues, and I look forward to hearing about the discussions and the follow-through that will come, particularly in the special volume of the journal Conservation Biology. I'm pleased to see that Christian will be presiding over today's symposium. Given the range of issues that you'll address, his skills will be tested. But I can assure you his mastery of science, as well as his skills at diplomacy, will be useful today. Of course, as Christian mentioned, we all owe a debt to Director Emeritus and Senior Scientist Ira Rubinoff. He was Acting Secretary of Science also, for his work at the Smithsonian Tropical Research and on behalf of the Smithsonian. His long-standing contributions to the Smithsonian have been a key to our science and intellectual advances. Ira, we thank you. And I certainly want to recognize our current Acting Undersecretary of Science, Charles Alcock, who is Director of the Smithsonian Astrophysical Observatory in Cambridge, and thank him for his leadership and support of the Smithsonian. Today's meetings, as Christian mentioned, had its origins actually in a workshop that was held last August at STRI by Bill, Laurance, and Joe Wright. And I believe that the success of this meeting will be much enhanced by virtue of what they've done to make this possible. From my personal point of view, this symposium represents the very thing the Smithsonian should be doing. Using our convening power and building on our long-standing research in biodiversity, we can join forces with colleagues from around the world to inform an issue that will impact the future of all occupants of the earth. In my humble view, it's slightly misleading to view this symposium only through the lens of the survival of the rainforest, because the rainforest and their health are integrally linked to the issue of climate change, which in turn is linked to matters of growing concern to all of humanity and the other creatures on this planet. In other words, it's critical that we understand the behavior of the natural system and how one piece of it affects another. The problems are not simple, not the least of which is communicating the complex science behind the dynamic processes, not only to do so to our fellow colleagues, but to express it in such a way that our political leaders and the public can understand it, so global action can be mobilized. I'm proud to say that the Smithsonian recognized the importance of this subject many years ago, and that our commitment continues. Our Center for Tropical Forest Science, which originated in Panama, has been a leader in understanding the changing demographic structure of tree populations. Our work is based on a network of large-scale forest plots for measuring the global impact of climate change on biological diversity and forest function. It has been in existence for decades and has expanded to include 20 forest research plots in 15 countries and 30 partner institutions worldwide. 3 million trees are monitored around the globe. Our newest initiative in this area is the Smithsonian Institution Global Earth Observatory, which will engage even more partners worldwide in this important effort. To elevate broad public understanding of the issue, the Smithsonian Natural Museum of Natural History, this museum, recently launched an ambitious online partnership, the Encyclopedia of Life, to create a web page for each of the 1.8 million species known to exist on planet Earth. More than 40,000 species pages are already posted and are available to the public and to teachers and students alike. In addition, scientists from this museum are active participants in the Barcode of Life project to identify plant and animal species, which is fundamental to our understanding of the differentiation of species on planet Earth. Finally, we are pleased that the Smithsonian's National Zoological Park and its 3,200-acre Conservation and Research Center in Front Royal, Virginia, has been selected by the National Science Foundation as a core site for the National Ecological Observatory Network, or NEON as it's known, which is a planned continental scale ecological observatory lasting for many years. Through the long-standing efforts of our scientists, the Smithsonian has been a leader in biodiversity issues. But our new and innovative large-scale initiatives that I just described represent our commitment to the future, to an era where science will reach a broader audience and elevate the profile of the issues, where we can help inform public policy, and where we can join in the collective global efforts needed to shape a sustainable future for all of us. It will take all of us in this room and many more to make a difference. So I thank all of you for being here and wish you the best of luck in your work. Thank you very much.
Thank you very much, Wayne. And let's get right to it with our symposium, our speakers. And I'd like to first invite Dr. Bill Laurance, who's going to give us an overview of the topic and some background for the symposium. And as I mentioned, Bill is a staff scientist at STRI, and he's known for a lot of his work related to deforestation, primarily in the Amazonian basin. Bill.
Okay, now, is this coming up? Okay, great. Well, thank you very much for joining us today. It's nice to see such a good turnout, and we're especially pleased to have a very diverse audience here, which includes a lot of people from government agencies and NGOs and the Smithsonian itself, of course, and we really like the idea of transcending the kinds of scientific audiences that we often talk about to people that are involved in real life decision making and in other aspects of life. So it's a great pleasure for us to be here, and I'll be happy to say more once you ready to go? I thought you were doing this. Am I doing this? Okay, I thought you were, okay. This is not what I want. Oh, this is it here. Okay. F5. Okay, great. And can we turn the lights down? Just turn the lights down? Yeah, great. Okay, well, what I'd like to do is basically say a little bit about what this is all about. Now, some of you, if you're scientists and if you're interested in conservation, you may have followed elements of this argument. Well, what I'd like to do is sort of in the spirit of bringing us all up to speed, to say a little bit, give a very quick overview of some of the issues that we're debating about here. I've been working in tropical conservation biology for about a quarter of a century now, and this really is, I think, one of the most important scientific type debates that has emerged in a long time. So I'd like to tell you a little bit about this and essentially saying, well, what is it that we're arguing about here? And there's definitely some different points of view and some different perspectives here. Before I tell you what we're arguing about, though, I'd like to tell you what we're not arguing about, because I think that's important as well. For example, we don't disagree about the fact that tropical rainforests perform a whole array of very important ecosystem or environmental services that are very important to making Earth a livable place. Tropical forests recycle a massive amount of rainfall almost immediately back up into the atmosphere. They're very important in terms of maintaining cloud cover, generating clouds, generating rainfall, which helps to make the tropics an ameliorated, productive environment. Those clouds also reflect a lot of heat, solar radiation, back into outer space, thereby helping to slow global warming. Tropical forests are also essentially giant biological sponges. You get thunderous rains in the wet season, and they trap that rain and they release it slowly, so you don't get, when you get a lot of deforestation, of course, you can get catastrophic floods down rivers of where you've had deforestation, and you can also get streams and rivers failing in the dry season. So they're very important in terms of their hydrological features. They're very important in terms of protecting the delicate topsoils that you find in many tropical areas. Without this vegetation cover, of course, the soil surface can just be stripped away and end up causing a lot of sedimentation and pollution in rivers and streams. And of course, they're storing massive amounts of carbon. Hundreds of billions of tons of carbon is locked up in these forests, in the living material. And if that's burned and liberated into the atmosphere, that, of course, is tropical deforestation itself is a major source of greenhouse gases, causing about 1/5 of all the greenhouse gases that humanity is spewing into the atmosphere today. And of course, finally, there's this stunning biological diversity of forests. I mean, somewhere probably upwards of half of all species on the planet are occurring in this ecosystem. It is truly the biologically richest real estate on the planet. And none of us disagree about the fact that tropical forests, particularly primary or old-growth tropical forests, are disappearing at an alarming rate, on the order of about 50 football fields a minute, or about 13 million hectares per year. And those numbers vary a little bit, and it depends on the definition of the forest. But the bottom line is tropical forests are vanishing very, very rapidly, particularly when we're talking about old-growth forests. So are we on the verge of a tropical extinction crisis? And I think many biologists have historically thought we may well be in this situation. And it's been argued by some biologists that, in fact, we may be facing a truly catastrophic loss of species that could potentially rival some of the 5 or so mass extinction events that have plagued the 5 billion year history of the planet Earth. And this is just one example right here. There's quite a well-known paper by Rodolfo Dirzo and Peter Raven, two very prominent tropical biologists, that suggested, for example, by the middle part of this century that perhaps only 5 to 10% of the old growth forest would be likely to survive. And if you use something called a species area curve, which is just a very simple relationship between how much habitat you have and how many species you have, if you sort of extrapolate into using those numbers, you come up with some kind of estimate that somewhere between perhaps 50 to 75% of all tropical species could either go extinct or could at least be committed to extinction as a consequence of this habitat loss. And so these are the kinds of numbers that have sometimes been thrown around. I think in many cases the spirit of what in some cases admittedly was a fair amount of hand-waving was in the interest of trying to increase the reserves and protected areas in the tropics and try to get people interested in the issues of tropical conservation. Now, Joe Wright and his wife, Dr. Helen Muller-Landau, have come up with a very provocative series of papers which have challenged this idea of large-scale species extinctions. And, you know, different people, you know, some guy on the street could come up with this and he'd say, I don't believe these numbers in tropical extinctions, and we wouldn't really be paying a lot of attention to them. However, people have paid a lot of attention to Joe Wright and Helen Muller-Landau because they're very prominent scientists, very successful, very well-known scientists. And in fact, Joe presented his initial arguments as his presidential speech for the Association for Tropical Biology and Conservation, which is really the flagship scientific organization in the world for tropical biology. So that was a very high profile for him. And they produced a scientific paper which got a lot of attention, and then they also produced a press release which was very widely distributed around the world. And if you just go on the website now and you start typing these things in, you'll see that lots of these websites come up which basically relate these stories of how, you know, that things may be more optimistic than we should think, and that tropical extinctions may be considerably less than people have extrapolated into the future. Now, this is a controversial issue, and different people, a number of scientists have had, as you will hear today, serious issues with elements of the Wright and Muller-Landau thesis and argument, and I'll tell you a little bit more about that here in a minute. And there's been a whole variety of rebuttals. This has really stimulated, in some sense, almost an avalanche of research. There's been a couple dozen papers at least produced in the last couple of years hanging off of this argument. But here's some of the more prominent rebuttals or rejoinders to their papers by Brooke et al., Gardner et al., Sloan et al., and then I had a paper sort of trying to synthesize the argument in a journal, Trends in Ecology and Evolution. And also I was fairly critical of elements of their argument here. But it was interesting to hear what the referees were saying about this. You know, we get our papers reviewed by anonymous referees, and they look at it very critically. And it's interesting to see the kind of comments that I was getting here, saying things like, referring to the Wright and Muller-Landau paper, their argument is just plain dangerous. We should hit them hard and with one voice. And I know you have to work with the Wright, but you're being far too diplomatic and nice. You know, as scientists, we're a little bit like lawyers. You know, we do and say the nastiest things in the nicest way. And when people start talking like this, it just gives you some sense of how high feelings are running in terms of an issue like this. And I would just like to say, look, I think we're having a very nice scientific discourse and discussion here. And I don't think it's appropriate to vilify anybody who would be involved in this debate and to, you know, to take a type of tack that's really counter to the levels of sportsmanship. And I'd like to emphasize that I would never stoop to myself personally engaging in any kind of vilification of my learned opponent, nor would I ever try to portray myself as somehow on the side of good in this particular discussion. Slightly more seriously, though, what I'd like to do is tell you briefly outline the particular argument or the guts of their scientific argument. And it's an empirical argument. It's a data-intensive, data-based argument, and all due credit to them to really changing the landscape of the debate and doing it in a data-rich way, which has challenged people, I think, to think much more rigorously, much more quantitatively about some of these issues and predictions. And one of the key elements of their whole argument is that if you look across most tropical countries, this is for 45 different tropical nations that comprise most of the tropical forest cover in the world, you see that there is a very strong negative relationship between the population density, particularly rural population density, and how much forest cover that you're going to have within that country. In other words, if you've got lots of people, you're not going to have lots of forest. It's a logarithmic relationship, which means that it's not actually linear, but it's a logarithmic relationship there. I emphasize here that it's they're looking at net forest cover, which includes all forest types. So this includes primary rainforest, but it also includes log forest and secondary forest and fragmented forests and even things like exotic pine plantations and exotic tree plantations. But the bottom line is there's this very strong relationship between how many people you have and how much forest you have. So that's kind of one of the key elements of their argument. Then they say, well, if you know how many people you've got, you can have a pretty good idea of how much forest you're going to have. So let's look at how many people we're likely to have in the future. And they then use the United Nations projections for future population growth. And the basic idea, of course, by having such a strong relationship between the number of people, particularly rural people, is that it's largely presumed in their modeling that it's small-scale farmers, slash-and-burn farmers, and small-scale rural farmers that are causing most forest destruction. And anyway, so if you look at these data from the United Nations, you see that yes, although global population has been growing at a breakneck pace, it is starting to slow down now. We're probably going to plateau somewhere in the order of about 10 billion people. But we are seeing that growth is beginning to slow down in some parts of the world, and also that we're seeing very indisputably a strong urbanization trend. People are definitely moving more and more into cities. We're getting more into some massive cities within the world. So you can see here, for example, going between 1950 and on up to 2030, using the UN data and projections into the future, that although the urban populations are projected to continue growing very rapidly, rural populations in general are predicted to plateau and perhaps even begin declining in some areas. And so, at least in Latin America and tropical Asia, Africa is a little bit of a different situation there. They're continuing to have very high rural populations. But then, so if you know basically how many people you're likely to have, that gives you a good idea of how much forest you're going to likely to have, or how much forest you're likely to lose in the future. And if you know that, you could then use something called the species area curve, which is a very basic tool. It's sort of a blunt instrument, but it's a basic tool for estimating how many species you have. And I've just illustrated a species area relationship here. This is showing area of land, increasing area of land on this axis, and this is showing the total number of species. So you can see here, and I just plugged in here some arbitrary values which are more or less typical from the literature. So we have, say for example, 5,000 hectares of forest would be predicted to support 64 species of, let's say, birds. And then what you generally find is if you lose 90% of the habitat, you typically will lose about half of all the species. So you can then use these species area relationships to say how many species are we likely to have in the future. And essentially they did this for the African tropics, for the New World tropics, and for the Asian tropics. And the numbers that they came up with were substantially lower than some of these very high 50 to 75% types of numbers that we've seen waved around before. They estimated, for example, that just 21 to 24% or 16 to 35% of all species would be threatened with extinction in the African and Asian tropics. And they didn't generate estimates for the New World tropics for some technical reasons, but they definitely think that extinctions there would be lower. And I underline they're threatened because, in fact, they don't think, as I understand it, they don't think that all those species would go extinct as a result of habitat modification because of some other factors. And these are the other key factors here, which is that some key elements of the arguments, they don't believe, I mean, this is probably almost certainly true, endangered species don't disappear immediately. There's many examples of species that whose populations have declined to very small levels, even very small fragmented populations that manage to cling to survival, oftentimes for longer than we think. Another thing is that because we're sort of seeing in general a depopulation of many rural areas as people increasingly move into the cities, that they see there being a lot of regeneration of formerly cleared lands, secondary forests regenerating, and they believe that those secondary forests will provide habitat for at least some of these threatened species, and so this is going to help to buffer the consequences of habitat loss, is effectively going to help to reduce extinction rates. And the third thing that they argue is that, in fact, we've already lost a lot of species from ecosystems because there have been, for example, there have been severe ice ages that have cooled and dried a lot of tropical areas. In the African tropics, for example, the Congo Basin contracted down into a much smaller area of forest than what you have today. In Central America, more recently, there's been strong human impacts, for example, in Central America. You had Mayan populations that cleared a lot of forest. There's been a legacy of intense hunting. And we know in many parts of the world, as humans have arrived, they've oftentimes killed off a lot of the large animals. They've killed off in Africa, or in North America, in Australia, New Zealand, lots of other places. Humans are blitzkrieg hunters that definitely kill things off. So the bottom line of their argument is that, hey, a lot of these species that are really extinction prone, in fact, have already disappeared. So we're probably not going to see that many more extinctions in the future. That's the key elements, in a very simplistic way, the key elements of their argument and what we're debating about now. A lot of these points are debatable, and you'll hear different people here address some of these issues. So anyway, I don't know what to call this, whether it's a debate, discourse, dialogue, diatribe, whatever it is, but I'd like to very much welcome you to this here today. And I'd just like to end by saying, look, this is really not about winning or losing. This is really just all about the science, and I hope you'll join me. Welcome, everyone. Thank you very much.
Thank you, Bill. We'll try and recreate that shot at the end, since we have both of them here. We'll see who ends up there. Okay, so let us start with our talks to explore some of these topics that Bill has just introduced. And the first talk is going to be by Gregory Asner. He is a staff scientist at the Department of Ecology at Carnegie Institution, and is also a faculty member of the Department of Environmental Health System Science at Stanford University. He's also been directing what's known as the Carnegie Airborne Observatory, which is a new observatory devoted to remote sensing and regional studies of ecosystem structure, chemistry, and biodiversity.
Well, it's a pleasure to be here, and I want to thank the organizers for the wonderful, well, all the way up to Bill's final introduction there. It's been a great gathering to try to come together and deal with some of these issues that are important to all of us and to the world. My job, in a sense, is a little bit easier than some of the other speakers. I've been asked to come and talk about the patterns of change. What are we observing? In particular, what are we observing in terms of land cover change in the humid tropical forests of the world? So in a sense, I have a bit of an easier challenge because some of this is not so controversial, although I am going to bring in a few issues about global forest change that are controversial within my community of trying to monitor these things from space and from the ground. I want to start with my messages. I want to start with the take-home messages of my talk. The first is that easily deforestation remains the dominant pattern of tropical forest change worldwide, and I'll show you that. We have no, as Bill mentioned, we have very little argument about that. I'm going to try to give you some facts and figures and some reality on that, though. The second one is that regrowth of tropical forests is actually substantial. There is a lot of regrowth, but it is in the vast geographic minority compared to the rates of actual gross and net deforestation. The third one is the one that is more controversial. It's one that I put a lot of my career into, is looking at other types of changes in forests besides the clear cutting associated with deforestation. And I'm talking here in particular about selective logging. You're going to find in my talk that selective logging is as widespread or even more widespread than deforestation itself throughout the humid tropical forests of the world. One of the things I'm going to kind of trickle through my entire talk is that all of these estimates and projections and measurements of whether it's deforestation, logging, or regrowth all come with caveats, scientifically based caveats that we publish quite a bit in our community, but that I'm going to try to explain here in the briefest of talks. And to let you know that most of those are related to satellite technologies, mostly the lack of a lot of satellite technologies that we're working as a community to develop. And then kind of my take-home messages is, at the end, I think you'll agree that in the face of this rapid deforestation and what I'll show is forest degradation beyond deforestation, that this safety net that we're talking about for tropical biodiversity is frayed and it's uncertain. And that's where the other speakers are really going to be able to chime in. I was also asked to make sure that I was speaking to the widest range of people, so I'm going to spend one slide on a few terms, starting with what is a forest. I know that sounds funny, but you'd be surprised in the international community how we argue over what a forest is. And that becomes important when we're monitoring these forests and looking for change. The UN FCCC puts a definition to it like this, and this is probably a good working definition for most, is that it's a minimum area of about up to a hectare is kind of, you got to reach some sort of minimum area for it to be considered a forest, or about 2.5 acres, with tree crowns that range, that cover the land 10 to 30%. And that range, the 10% is the official UN number, but certain countries would like it to be 30%, so I give the range. And then they contain these trees that are 2 to 5 meters tall or taller. So that's what a forest is, according to the UN. What is deforestation, according to the same body, is direct human-caused conversion of forest to less than this 10 to 30%, depending on what country you're in and how it's being defined regionally. What is selective logging? The International Timber Trade Organization defines it as partial removal of trees for timber or for forest management. And the last definition is, what is regrowth? You're going to hear us talk about that quite a bit today. It's the recovery or increase of forest canopy in this height range of 2 to 5 meters or taller. It's these basic definitions that form the basis for the global monitoring that people like me and a lot of my colleagues are doing. I want to also spend a minute to say, when we think about tropical forest change, we have to think about it in the larger context, and I think Tom Rudell is going to hit the drivers of forest change much more than I will. But I wanted to point out one thing, is that if you think about it, any region of the world, any country, any economy, you're really talking about that economy or that place in the world being somewhere along this continuum of land use transitions, from natural or frontier ecosystems on the far left to clearings to subsistence production systems, small landholder agriculture and whatnot, to where we are, say, here on the east coast of the U.S. in this intensive system that has relatively small fraction of natural systems, large agricultural investments, large urban areas, and some fraction of protected lands. You can think of this deforestation issue and these forest change issues along this continuum from, say, closed canopy primary forest in the first image to these frontier clearings that we're talking about at different stages of the discussion today, to this subsistence agriculture that's moving around on the landscape. And ultimately, in some cases, and believe it or not, here's an image from the central Amazon, the state of Mato Grosso, even intensive agriculture, and now in what was humid tropical forest. You can see these types of transitions expressed in satellite imagery. You can go to Google Earth, and if you zoom in and take a slow look around Google Earth, you'll see some of this stuff. On the left side is an old image from the central Brazilian Amazon in the state of Rondônia. And you see in the upper left of that image the fishbone pattern of deforestation. That pattern is and was in this region a pattern associated with lots of small landholders coming in and grabbing a piece of real estate to develop their cattle ranch or a small crop or whatever it would be. And on the right side is an area in the Bolivian Amazon with large landholders that are now consolidated at some level, and most of the forest cover is gone. You can go through and look through time and see on a single image small landholder activity in the northwest and large landholder activity developing in the southeast in this area in Mato Grosso. And you can come back and see a major land use transition that went from predominantly smallholder type activity on that chart that I showed to this one dominated by large industrial grade crop production. And Tom's going to hit, I believe, some of those issues. Along the same continuum, you can also talk about regrowth. Forest regrowth comes at least two different ways. One is on purpose. Somebody clears some land, uses it for a while, and then releases it back to nature. You might see that in frontier clearings. Another reason why regrowth occurs is the inefficiency of the human enterprise in tropical systems is one where it's kind of hard to keep an area cleared in some of these places. Plants do grow, and it takes a lot of human power and effort to keep an area cleared. So as you go along this land use transition matrix in any given region you might be concerned about or know about or read about, think about regrowth being potentially occurring. I would say that the amount of regrowth along this transition, the potential for regrowth actually decreases as you get towards more intensive agricultural systems that are under heavy use. And that's why the shape of the regrowth triangle decreases as you go to the right. One of the key questions that I don't have to deal with directly in my talk, but that everybody else does, is what is the biodiversity response to these transitions? You can imagine this graph showing a change in forest cover. One of the big questions we have to deal with as a community is where will those species go? Will they come back if the system is allowed to regrow on the upswing? That's the big question. So with that in mind, I want to talk for a few minutes about deforestation and then logging and some other issues and regrowth, and give you some of our latest facts and figures so that you have some reality as to what we think as a science community is going on out there. The measurements of, or estimates really, of deforestation prior to 1980, back into the 70s, 60s, and prior were rough. They were not based on satellite technology. They were based on census and estimates and visits and whatever else it took to try to get some idea of what was going on. These deforestation rates I show here by continent or subcontinent are in percents. So Central America proportionally was going through very high deforestation rates according to the FAO in the 70s. South America, about half that proportionally, but it's of a much larger area, so you have to think about that when you look at percentages. A little background. Frederica Shard and others at the European Space Agency put out in 2002 a major study on global rates of deforestation. And you have to understand that when you do global type mapping, you can't see the smallest types of deforestation. You see things that are about 25 hectares and larger, or that's about 60 acres and larger. Okay? And what they came up with were some important numbers here. The red is deforestation, and the green wedge of the pie is their estimates of regrowth. And what you see, for example, in the Americas is 2.5 million square kilometers were cleared in the 1990s, in particular between 1990 and 1997. So moving forward through time here. And there was a fraction, although very small, that was measured as regrowth. And you can see this for different continents and subregions. Asia and Oceania went through a similar level of deforestation and regrowth. And then Africa is lagging behind. One of the key things is that those numbers don't resolve the extreme variation by state, by not let alone country, but by states and municipalities and all the sub levels within any given country. And these are just some numbers that I think are interesting, just to get a range of the percentage of deforestation that was occurring in different regions of the world. What happened between the 80s and 90s? Deforestation actually did increase. People say, is it increasing or is it not increasing? Year to year, it's kind of like climate variability versus climate change. Year to year, we see ups and downs. But decade to decade, for the few years for which we have satellite monitoring, we saw an increase. And I'll tell you ahead of time that in this decade, we're beating the last 2 decades. And you can see this expressed here by Ruth DeFries's work. She's at Columbia U. She's led a series of papers on this. She's converted these into carbon emissions, forest cover to carbon. But you can see that on all of these subcontinents and continents, the amount of carbon lost went up. Here's some of the latest estimates of deforestation from 2000 to 2005, just to kind of wrap up the deforestation. And you see areas where at least 10% of the forest is lost, 1 to 10%, and less than 1. And what you really see is huge changes in the southeastern part of Brazilian Amazon, and very large changes in Borneo and other parts of Oceania and Indonesia, shown in yellow. I think you can sum that up and look at it with numbers and facts and figures. I think some of the most intriguing results are on the bottom line. We think that there is about 20 million square kilometers of humid tropical forest biome that was there. In just the last 5 years, that's the middle column, we've seen 1.4% of that region gone, cleared, in 5 years. And as of today, or a few years ago, about half the biome which is the second to last column, half the biome has trees only covering 0 to 50% of the forested land. Remember I told you about the, I should say 10 to 50%, that's incorrect. I told you about the FAO, I'm sorry, the UN calling a forest 10% or above. Well, there's half of it is less than 50% tree cover, and half has more than 50% tree cover. So the system is highly fragmented and is not as pristine as a lot of people think. What about regrowth? One of the big issues that you're going to hear about is regrowth comes in kind of many flavors. One way to think about it is short-term regrowth versus long-term regrowth. Short-term regrowth in terms of biodiversity is a very different set of outcomes compared to long-term regrowth. If a system is going through clear cutting every 5 years, the species that are able to inhabit that system, it's vastly different than one that has gone through a single cutting and is going to be left for regrowth for the long haul. Another one is the spatial distribution of this regrowth. That was time, this is space. The system on the far left is one where if those pastures were abandoned, you could imagine that the system might fill in and there would be good recovery in those systems potentially. Whereas the system on the right is surrounded by a sea of urban and agricultural systems where there isn't a lot of biodiversity source for expansion outward from that one core that's left. And finally, from the satellite perspective, one of the hardest things about studying regrowth is that regrowth is usually a gradual process that's hard to pick up on satellites. The only way to really pick it up is to have very continuous satellite measurements. That's very hard in some humid tropical regions. This map of the Brazilian Amazon shows the probability of getting cloud-free imagery in some of the states of the Brazilian Amazon. This is based on 54,000 Landsat images. The areas that are dark red are essentially you have no chance of getting an image of that area that has 10% cloud cover or less. So just the ability to take a picture of it from space is very challenged, and therefore it's hard to follow these changes through time. Some people have done it pretty well. Small island of Puerto Rico has gone through radical changes from 1951 to 2000. You see regrowth occurring as dark green areas increase in area and the light green areas fill in. So there are some emerging examples of regrowth. My group, some of which are represented here, decided to use a literature review to try to pull together all the regrowth estimates. And what we found is that most of the regrowth reports are coming in from South America and Asia, almost none from the central part of the Congo basin, and a few from Madagascar. What's interesting, and again I think this will be talked about, is most of the abandonment and regrowth is in mountain and hilly terrain and not in the lowland environments, and I think Tom will speak to why that's the case. So just adding to the chart, we have our biome extent, different continents. We have the amount of cleared land in just 5 years, 1.4%, so careful here. And then we came up with the area regrowing of 1.7%, but it's strewn over 20 years, okay? So you get about the same percentages, but on different time scales, 5 versus 20 years. So you can almost start to think, well, that looks like the other data you saw from Frédéric Achard. About 25% of the system is undergoing regrowth, potentially. The regrowth is our most uncertain estimate. What about other forms of forest disturbance? We know there are many, besides deforestation. Weather events and herbivory. There's Hurricane Iniki passing over me on Kauai in 1992. Human activities, we heard some of these earlier in the introductory comments, from invasive species to fire. The one I want to talk about is selective logging. Why? It's ubiquitous, and I'll show you how that's true. And it's an example of potentially a forest use rather than forest clearing, so it has very important economic potential. The question is, what is the style of logging that's going on out there, and what are the effects on biodiversity? Logging intensity varies widely. You're not going to see helicopter-based logging in the top left very often in Latin America or Southeast Asia. It just doesn't occur. No one has the kind of money for that. What we see more often are the middle two types of logging intensities, from road building and extraction in the lower left to kind of the much higher intensity logging in the upper right. Those are the two that I've seen all over the world, over and over and over again. You rarely see the clear cutting for just logging. Usually it's for something else, like agricultural development. Logging is extremely difficult to map from space. On the left, it's easy to see that kind of clear cutting from space, as I showed you. It's pretty routine now for the science community. The logging is cryptic and involves just a thinning of the forest. You can imagine looking at a map like this and seeing the addition of newly cleared areas in red, green, and blue in this portion of Mato Grosso as an example. The question is, if you zoom in on one of those polygons where there's been a deforestation event shown in yellow and brown, what else was happening in that image that wasn't seen with the older technology? Here's an example from the same exact moment in time, taken from space. The left using the older technology for deforestation, and the right using the new technology that the community is using for finding this kind of cryptic deforestation, and you can see a much larger human impact. The blue area shown, that kind of helter-skelter, are all the types of understory skid trails and networks that are built by loggers to pull the wood out of the forest, even though it still has a predominantly green canopy on top. Here's another example. It looks like a relatively pristine forest. The new technology shows it for what it really is. Systems that are radically affected by the logging industry and the kind of heavy logging practices that predominate throughout the world today. Here's another one that shows the progression of logging across a landscape, a large 1,500 square kilometer landscape in Amazonia. The deforested lands shown in purples and reds are pretty static over this 3-year period. It's cycling through 99, 2000, 2001. But what you see is this movement of loggers through the forest. Each of those is a large logging event. My group put this together for the first time ever in 2005 and looked at logging throughout the Brazilian Amazon, at least the states of the Amazon where logging was economically really happening. And you see for the first time in reds, greens, and blues, depending on the year, kind of the intensity of logging throughout the region. In this group, for this symposium, we were asked to try to apply some of those techniques and those pattern analyses worldwide for the first time. And you're seeing it for the very first time. Logging the amount of forested that's either being logged now, recently logged, or in timber concessions. I would call that destined for logging. Those are the red polygons. Zoomed out at this level, we can only show outlines of them rather than all the details. The take-home message is that if you go to the far right side, selective logging compared to the other forms in terms of deforestation and regrowth is massive globally. And these numbers roughly correlate with the amount of wood that's coming out of these forests for markets. About 5 million square kilometers has somehow since 2000 either been or will be logged in the near future. That's a huge 28% of the biome. You can look at these, to finish up in a slide or two, you can look at the juxtaposition, the pattern of all of these types of forest change, and you see that they're not completely independent of one another. In the Brazilian Amazon, there's this kind of human pressure moving inward and to the northwest, and you see that in the hatch marks of logging, the red of deforestation, but a wake of blue dots, which is the regrowth, the inefficiency, or the release of some of those lands back to regrowth. You can see it in the pattern on the map. That's the first time that's been shown as well publicly. And my final slide is kind of to say, well, those are all the patterns that sets up this group to talk about what's going on in terms of the biodiversity response. I think 2 issues on the patterns, though, of the future you're hearing about, I'm sure in the paper and wherever you might read about carbon credits and whatnot, is that we're seeing kind of these 2 major phenomena, one of biofuels development increasing in the humid tropical regions and is a potential driver of deforestation itself, kind of juxtaposed to this issue of carbon credits through this program called UN RED for reduced emissions for avoided deforestation and degradation, that potentially these same regions could be getting credit for the carbon that they sequester rather than cutting it down. These are going to be the 2 forces, I think, that are going to drive and continue to drive the patterns of change beyond what I've shown you in this decade. Thank you.
Let's see if there are 1 or 2 quick questions to clarify. We're going to have the debate at the end. But if there are any particular quick questions at this point from Greg. Of course, I can't see any of your hands, but Okay, yes, Joe.
You mean the rates and size amount in terms of square kilometers? Yeah, the question is, I think it's to summarize is the question, the rates of deforestation. Okay, thank you. Yeah. Yeah, so one of the big, thank you for allowing me to say this, one of the big issues here that I failed to highlight is the global deforestation is becoming a routine. There's uncertainty, but I think that we can rely on the numbers. The regrowth, the exact opposite is true with the regrowth estimates. It's highly uncertain. We don't have the kind of satellite technologies that really let us look at that, so we're relying on the literature. The literature that we were able to find are naturally focused on regions of interest to scientists. So those dots on the map are not all of the regrowth in the world by any means. It's just what's been published. And we're sure that there's a lot of regrowth going on that isn't published. So those are some of the major caveats. What we can see with satellites in terms of deforestation, we just are not ready to be sure with the regrowth part of the curve.
Another quick bit.
That's right. And so the question was the short versus long-term regrowth, and we're even more uncertain than even what I just said, and that's true. I failed to say that those rates of regrowth were, the reason why we're spanning 99 to 2000 in that example is we tried to only select papers and reports that are reporting long-term regrowth. So that was that. What we're not looking at in that table is the short-term regrowth. However, some of the satellite technology, like the Ashard study that I showed, was sensitive to the short-term stuff. And so it is an issue. It's a debatable issue. How much is really regrowing? I think our estimates are conservative. They're long-term in the reported areas. So I would have to err on those with the conservative numbers.
All right, I think we're going to move on. Thank you, Greg, and we will come back and you'll have another chance to comment on these issues. Having spent many hours of my life at some UN meetings, I appreciate the definitions that you put up, and believe me, a forest is not always a forest, and measuring it and debating is big, but I think as we look at climate change issues going forward, as you mentioned, this is going to be a very big issue, for and against it. The next speaker is Tom Rebuttal. He is a professor of human ecology and sociology at Rutgers University. As you read in his bios, his life was changed early on by his experience in Ecuador, and he's going to talk to us about the agents of extinction, do historical shifts, and who exploit tropical rainforests, provide new opportunities for conservation. Tom.
Okay, well, thank you, Christian and Bill and Joe and the Smithsonian for organizing this event. I hope it helps focus us in terms of our thinking on extinction crises. And just to begin, what I'm going to be talking about, first of all, I'm a social scientist. I'm going to be talking about the changes in the constellation of forces driving deforestation, in particular the historical changes. And I should say at the outset that in some respects, going from Greg to me as a presenter is like going from the sky above to the mud below. I first began thinking about deforestation when I was in the 1970s, when as a Peace Corps volunteer, I was helping some then landless peasants in Ecuador mow down some rainforest. And so I have my share of environmental sins in my background. Just to begin, the main message today, though, from me is really going to be a historical one, and that is that the forces driving deforestation have changed over time in significant ways, and in particular ways that are significant for the conservation opportunities available to us today. And beginning about 1945, one would have to say that the chief protector of rainforests historically were passive protectors in the form of physical impediments to getting at those rainforests. And what we have here is a shot of the Upano River in the Ecuadorian Amazon, and it's instructive here because for decades there was virtually no deforestation on the right bank of the river and lots of deforestation on the left bank of the river. And the chief reason is that people could not get across this river reliably. It runs fast, so dugout canoes were difficult, and try getting across that river with some cattle. It was virtually impossible. And as a result, the forests on the right remained intact for decades until a bridge finally crossed this river in the early 1980s. Okay, beginning in the 1960s, that's really the period from which the recent sort of spasm of deforestation dates. And it's a pattern that's driven by two forces. One is population increase, and this, you can see the intellectual foundations of the Wright Muller-Landau model here. After World War II, you have relatively dramatic drops in rates of infant mortality in rural areas in Latin America and Asia, and 15 to 18 years later, you see real increases in the rates of household formation in rural areas. And oftentimes these people are going out into areas, looking basically for new lands to farm. And so you've got population growth driving deforestation during this period. But there's another force at work, and that's the state. Governments in the post-World War II era are concerned about securing their sovereignty over remote forested rural areas, and so they begin to spend money on colonization schemes, new land settlement schemes. This is driven in part by the fact that at least in most Southeast Asian countries, there are rural insurgencies in these areas. And during the 1960s, after the success of Castro's revolution, there are insurgencies beginning in remote rural areas of many Latin American countries. And so the government is, in some senses, through these colonization programs, trying to exert control over these areas. And in Ecuador, it led to an attempt to settle this particular area of southeastern Ecuador. Now, if you think about this just for a moment, this particular village, it's a colonist settlement, is 3 days, at the time of the shot was taken, is 3 days walk from the nearest road, and these are not exactly what you would call ideal agricultural lands. So you might say, well, why are people going out here? Well, in part, they're going out here because, first of all, they're landless. There's nowhere else for them to go. Cities do not, at that point in time, have large urban labor markets, and they are used to farming. And also because the state has promised to build a road out into this area. And in part, they're doing that to establish Ecuadorian sovereignty over this particular piece of land. So you get people moving out into this particular place. And I should mention, this is more or less where the Andes meets the Amazon. It's about 400 meters in elevation. It's malarial. Not in many respects a place where many people would want to live. And so the state provides some assistance. Well, some of the assistance came, okay, in the promised road, but this is a particular cable that they stretched across the river. You get to sit on this T-bar and go across it. I once did with a piglet strapped to my back. A memorable moment. When deforestation occurs, it's decidedly low-tech, labor-intensive sort of thing. You've got people going in there with machetes followed by axes. I think Abe Lincoln probably would have recognized the method. And as Greg mentioned, the spatial signature of this kind of labor-intensive deforestation is the fishbone. Here you can see the penetration road in Rondonia. Here's the farm to market roads built off the penetration road, and the farms off the farm to market road. So to sort of summarize at this point, what you've really got going on is what's this particular causal model. Rural population growth combined with rural insurgencies leading to state-assisted smallholder land development in rainforest regions and accelerated losses of tropical forests. In this particular context, conservation opportunities are by and large not there. So ecologists were beginning to raise the alarms about deforestation, but there was virtually nothing in the way of effective conservation responses during the period of the 60s, 70s, and 80s. Okay, but things have changed. And what we really have seen over the last couple of decades is the evolution towards a new sort of enterprise-driven pattern of deforestation. And a couple of things to note here. First of all, the old dynamic loses force. Insurgencies decline. At the same time, state debts increase, and new land settlement schemes are expensive programs to run. And more people are moving to urban areas, so from a political point of view, the center-left parties begin to think in terms of subsidies for urban residents and less in terms of programs that meet the needs of rural peoples. And so state assistance to small farmers declines. At the same time, trade is globalizing. You've got African timber going to East Asia. You've got Brazilian beef going to Europe. Rural to urban migration is increasing because now urban labor markets are larger. Urban consuming populations have grown, fueling the demand for lots of commodities produced in rainforest regions. And finally, deforestation concentrates increasingly in two countries, Brazil and Indonesia. And in the already deforested areas, as Greg pointed out, you've got uncertain amounts of regrowth occurring. So that's a series of changes that really sort of transform the driving forces behind deforestation since the mid-1980s. So you've got large expanses of rainforest being cleared by some of these much more highly capitalized enterprises. And so you've got, as Greg pointed out with some of his slides, this one is one from Indonesia, from Kalimantan, you've got blocks of deforestation occurring now. And if you're trying to model this, then basically what you want to do is begin with augmented consumer demand, expansion of markets to global scales, leading to increased amounts of logging, larger scale, more extensive cattle ranching, and the appearance of fairly extensive new kinds of agricultural operations focused on soybeans and oil palm, all of which produces accelerated losses of tropical forests. Okay, and at the same time, you've got the deforestation concentrating. You've got regrowth actually spreading. So, and as Greg pointed out, it's occurring in uplands, but it takes different forms in different places. And some of you might say, well, wait a minute, this isn't regrowth. But anyway, it's something definitely to talk about. You've got spontaneous regeneration going on in Latin America, especially in places with labor-intensive agriculture like coffee. You've got agroforestry going on in peri-urban and upland African settings. And you've got tree plantations being created over extensive areas of upland South and Southeast Asian countries. But the first point to note about regrowth is that it occurs in a wide variety of ways with different local explanations. This is a couple of slides of how it has occurred in one particular place in the Ecuadorian Amazon. In the late 80s, this is landside images, you've got some cattle ranches, the pastures are in yellow here, and you've got fairly extensive horticultural operations they're in pink. A pest runs through that area in the early 1990s, leading to widespread crop losses by the growers, and they begin owing the banks a lot of money. They then migrate to places like the United States and Spain, and by the late 1990s, you've got a landscape that looks like this. A lot more extensive pasture, very little in the way of citrus fruits that were afflicted by the pest, and in this light green, the beginnings of regrowth in association with these pastures. But this is in a mestizo community. Here again, and this is a shot from the ground of the same area, you've got secondary forest here, and here you've got a transition from a sunny to a shade-filled pasture, something that's also going on in this area, and I think is related to changes in the pasture management practices after a large number of the men migrate. 20 kilometers away amongst the Shuar, you find they're Amerindians, you've got a similar kind of pattern going on, at least in terms of the landscape, but for very different reasons. This is a Shuar community. This is a late 80s shot. You can see the pasture here along the main trunk line road. And then this is a shot 10 years later. And again, you can see a proliferation of light green. That's secondary forest. What happened here was the Shuar, in order to gain control, titles to their land, cleared a lot of land, planted pastures, got title, but then didn't have the financial resources to actually stock these pastures with cows. So the pastures began to go back into secondary growth. They then began cultivating the secondary growth in a kind of short cycle shifting cultivation, producing things like manioc and bananas for urban markets. And not surprisingly, in this kind of context, you've got people beginning to plant coffee and nurseries beginning to sell coffee seedlings to local smallholders. So what to do? I mean, where are the conservation opportunities in this particular story? Well, I think the most important thing to take out of this in terms of the politics is that it is right here, this last sentence. And that is that the most likely conservation policies in terms of getting success are going to be those that build on changes in land use patterns that are already underway, because there's a political constituency there locally who will try to promote these particular conservation initiatives. Let me just mention a couple of them. One is, now we've got deforestation is geographically much more concentrated than it used to be, 2 countries, and it's also concentrated amongst larger enterprises or amongst smallholders who are now organized into associations of landholders. The smaller numbers of people doing the deforestation creates opportunities for negotiation, direct negotiation with the people doing most of the damage to the forests. These kinds of negotiations, amongst the other things that one can bargain about, might be PES, payments for environmental services, green images, access to preferred markets, meaning markets for organic or certified products, and hopefully compliance with international agreements. This is a kind of opportunity that was not available during that earlier period of deforestation, where we had smallholders driving the patterns. Because you've got areas that are depopulating, there are conservation initiatives in those sorts of settings that probably would meet with less political opposition, in part because of the depopulation going on. Now you might ask, okay, well, won't the recession that we're in the midst of lead to a reverse migration and a re-intensification of this older pattern of smallholder deforestation at the same time that it slows down the enterprise-driven patterns? I mean, this is almost pure speculation, but it's certainly too soon to tell. But at least from this one area in Ecuador that I know well, it's not necessarily true that the people who migrated out of these the smallholders who left this region to go work in the U.S. or in the cities are going back to the exact same place. So to assume that smallholder deforestation is going to immediately increase because of the loss of economic activity in the urban centers or in the developed countries is open to question. It is conceivable in some that, at least in the case of certified, when you're talking about certified agricultural products, that the return migration may provide some labor for various sorts of organic agricultural products. Okay, let me just sort of recapitulate here, and by just talking about the experience of this second pattern of deforestation in one place. This is a shot of Macas, Ecuador, in the southeastern Ecuador. And a couple of things to note. First of all, Macas is a destination for rural to urban migrants and also return migrants from the United States. So you've got urbanization going on here. Across the river, you've got a plain where there's continued deforestation for cattle ranching, except on the more marginal lands that begin to verge into the uplands, and there, in those sorts of places, you see continued outmigration and some regrowth. And finally, in the mountains here, you have a forest reserve that was established in 1990 by the Ecuadorian government. So it's, again, a pattern of conservation in the uplands, continued deforestation in the lowlands in the midst of continued or strong urbanization impulses. So let me just sort of end on this note. I think one of the crucial issues here is figuring out how to turn this incipient, this sort of spontaneous regeneration that is going on to some sort of policy advantage to further conservation aims. So really what I think we need to understand better is what's driving, what sorts of policy opportunities are available in the regrowth that is occurring, and how can we use that to advance our conservation goals. Thank you.
Same drill. Let's see if there are a couple quick questions to clarify things, and then we'll come back. Yes, I think I see in the back. I can't see your face. So. Let's do a brief answer. This is more appropriate for the panel and the debate at the end. So, but if you want to say something brief.
I mean, you're certainly correct to say that the government has been selling all the subsurface mining rights in the southeastern Amazon. That's definitely correct. In terms of the overall landscape, though, one thing one needs to note here is that these mines, when they open up, do have a fairly localized impact. I mean, Nambiha is probably the primary example of this, but it is something to bear in mind.
We can come back to this when we open the debate. Bill, question?
It would seem to me that the Wright-Landau model is built on a period-specific association between population density and deforestation rates. And what would be interesting to do would be to see if, and I haven't done this, would be to look at whether or not that relationship attenuates over time going forward, going from, say, the 1980 through 2005 or 2010. The difficulty is, of course, the one that Greg alluded to about the quality of the data. It sort of hamstrings us in terms of building these sorts of historical models.
Okay. We can come back to this later. Tom, thank you so much for reminding us about the people in the landscape. All right, our next speaker is Robin Shaston. Robin is a professor at the Department of Ecology and Evolutionary Biology at the University of Connecticut. And let me just, this way of anecdote, say many years ago I had a chance in Costa Rica to visit at La Selva some of the plots that Robin had in secondary forests. You're beginning to get the point that the regrowth is part of the equation here, clearly. And all I'll say is I never looked at a secondary forest quite the same way. So, Robin.
Now, I'd like to invite all of you to come to Costa Rica to visit my secondary forest.
Wrestling match.
Well, thank you, Christian and Joe and Bill, for inviting me, for organizing and inviting me. And allowing me to participate in this sharing of ideas and information. I'm going to kind of bring the topic back to biodiversity. And my topic today is really going to dwell on the prospects for conserving biodiversity within the human-modified parts of the tropics. And most of the emphasis on conservation has been on protecting intact reserves and pristine forest areas. And I'm hoping that I can convince you that we need to go far beyond that. I'm talking about an extensive, very wide gradient of different types of landscape modification here, ranging from intact forest all the way down to areas where there's barely any natural habitat left, or just little relics or remnants. And along with this gradient, we see increasing fragmentation and edge effects such that the conditions within remaining forests are highly altered. And we also see a decrease in the connectivity, which is going to have serious impacts on the ability of organisms to move around and colonize areas of regrowth. So you can imagine the huge array of effects that these kinds of modifications have on biodiversity. Well, the fact is that most of tropical biodiversity is living outside of protected areas and protected reserves. In the Mesoamerican area where I've been working, 80% of the forest has been converted to agriculture. And what we see in most regions are scattered remnants of forest, remnant trees, small patches of forest cover, and areas that don't resemble what your typical conservation area might look at. But in fact, these are the areas where we are going to need to conserve most biodiversity. This is just an example throughout the world of different types of modified landscapes here in southern China, in Mexico, in Suriname, and in Bali, and all over the world we see a wide range of different types of human modifications. Many of these modifications are compatible with conservation of substantial levels of biodiversity. There will be some species, and I'm going to call these the most vulnerable species, that require intact and large areas of forest, for the most part protected areas, for survival. And these are the species that we are going to lose from large areas if we can't protect forest. But this does not mean that we're going to lose everything. And there's been a number of studies, in particular studies of birds, but we're increasing the number of groups that are being investigated. One such study done in Las Cruces area of Costa Rica showed that nearly half of the birds native to the area occurred in the deforested countryside. These would be areas of patchy forest cover, mostly pasture areas with scattered remnant trees. So I'm going to explore a little bit, where do we find the biodiversity in these landscapes? What are the kinds of habitat components that we need in order to maintain biodiversity and allow it to persist, and even to invite more biodiversity to come in and take up residence? Some of these are remnant forest patches. We've already seen some images today of smallholder agriculture landscapes, which still have lots of remnant forest patches existing. These may not necessarily be pristine forests, but they have a lot of complex structure and still have lots of biodiversity in them. We also see riparian strips. In many countries, protect areas on either side of streams, and sometimes these are the only forests remaining in certain landscapes. We also see patches of secondary forest regrowth, and I'll be talking a little bit more about that in a while. Forest plantations and agroforests, and living fences, which are prominent in pasture landscapes. And these are actually very important for movement of birds and bats and primates. We can also ask what kinds of species are present in these human-modified landscapes. And you might be surprised in order to find out what people are finding. Basically, we can divide species in three large groups. We can look at species that are specialists on disturbance that really do thrive in open, disturbed areas. You may recognize some of these creatures. We also have species that like forest, and they don't really venture outside of closed forest areas. And you might not expect to find them in early regrowth or in plantation type situation. Then we have groups of species that, for lack of a better term, I'm calling generalists. And these are species that you pretty much find in any kind of forest or disturbed forest habitat. They're not very particular. As long as there's some forest cover around, you're likely to find these species. A lot of these are species that tend to like forest edges. They might enjoy gaps in an intact forest, and then they might also occupy edge habitats in disturbed areas and secondary forests. The problem has been really trying to figure out what category species are. It's, you can't just look it up in a book and find out what kind of specialization or lack of specialization a species has. And we're very limited by the kind of sampling that we do on the ground to get this information. We can look at the forest biodiversity in a range of these landscapes in terms of the structural complexity. And we see that the structural complexity of the vegetation is a very strong determinant of the level of biodiversity that can persist. The maximum case of structural complexity would be an intact, mature tropical forest, which has many layers of foliage. It has many opportunities for nesting, for roosting, for protection from predators, for all kinds of complex lifestyles to exist. And that will maximize biodiversity. As we decrease that structural complexity through human modifications, we lose components of the system until we get to a situation like a pasture or a soybean field that is basically devoid of biodiversity. Well, we can build structural complexity into ecosystems that humans are using, such as agroforests. Here we have a range of different types of coffee production systems along an intensification gradient, from the modern monoculture, unshaded sun coffee, all the way to the rustic or traditional multi-layered coffee plantation, shade-grown coffee, which is basically planting coffee beneath an intact forest canopy. And farmers also will grow additional crops there with the coffee in a polyculture. These types of ecosystems can really provide a lot of the structural complexity that forests do, and surprisingly, we find a lot of the same species growing in them. In this study done in Veracruz, Mexico, the amount of shade and the epiphyte cover — epiphytes are plants like bromeliads that grow up on trees and branches and are important for foraging for a lot of species — and the height of the canopy are all important predictors of the bird species richness across this intensification gradient. These three sites on the left were intact forest, and there's two types of bird species here, the forest species and the generalists. These two sites are traditional shade coffee plantations, where you have both forests, the same number of forest species, a few more generalist species, and we've picked up a few open species. These sites actually have more species richness than the forest. As you go to more commercial polyculture and into the monoculture systems, there's a decrease in the forest species and an increase in the generalist and open species. So we see the importance of having heterogeneous forest structure and components that we find in the forest system. Bagwat et al. Did a survey of about 36 different agroforestry systems, and I just want to summarize their findings here. They found a significant role that these ecosystems can play in protecting species outside of formal reserves. The green bars here show the species richness as a percentage of the forest values. So this would be matching the levels in the forest at 100. They actually found more bats. And some other groups of organisms showed fairly high representation of biodiversity. The lighter green bars are the similarity, the composition of the species, and we see in this case that not all of the species that are present in the forest are present in the agroforests. But in some groups, there is a considerable amount of sharing going on. So it's a mixed story, but we still can protect a lot of species within these ecosystems. and use them for agricultural products. Another good example are the areca nut palm plantations in the Western Ghats in southwestern India. And this is an area that has been cultivated continuously for over 2,000 years. So this isn't just a recent land use conversion. This is a long, long-term relationship between humans and the land. And in these areca nut forests, 90% of the bird species that are associated with the regional native forests have been retained. So there's still a very rich fauna within these forests. Finally, I'd like to mention another system, which is a cacao or chocolate growing system in southern Bahia in the Atlantic forest region of Brazil. And I want to highlight this because this is a region of Brazil that has exceptional biodiversity. It's very well known, the Atlantic forest region. But only 6.5% of the old-growth forest remains. And in many parts of this area, many regions, the only forest cover that is left are these cabruca growing systems with intact forest canopy on top and chocolate trees growing in the understory, and sometimes mixed with polyculture. So you can imagine, being the only sources of forest structure in the area, these play an extremely important role in conserving biodiversity. In areas that still have remaining intact forest cover in this region, these cabrucas harbor a very large percentage of the local species. The groups that have been looked at so far include ferns and butterflies, lizards and frogs, mammals, birds, and bats. By no means is this a full inventory of the biodiversity, but you can get the picture that these cabrucas are essentially harboring a very high percentage of the native biodiversity. And for those of you who either play a string instrument or know someone who plays a string instrument, the wood that's used for the bows for violins and cellos and string bass is the Brazil wood tree, or the Pernambuco tree, shown here. And this is endangered in Brazil, and it's interesting to learn that this is one of the species that is present in the cabruca system. So this is one of the areas where you can still find these trees. Finally, I'd like to mention pasture landscapes, because these are extensive throughout much of the New World tropics in particular. And we tend to write off pasture landscapes from a biodiversity perspective. However, I don't think we should do that, because there's evidence that there's substantial biodiversity in many of these landscapes. This is based on some work done in a dry forest landscape in Nicaragua by Celia Harvey and her group. There are lots of trees in these pasture landscapes. They are not barren. They're not nearly as barren as the soybean plantations that you see in Mato Grosso. In fact, 50 different families of trees were found on these pasture farms, and 46 of these species were typical of forested areas. These are not particularly highlight or open requiring species. They're found in secondary forests, in riparian strips, in living fences, and in remnant patches of forests on these farms. This tree flora represented over 50% of the tree species that were reported for dry forest regions in the northern Pacific of Costa Rica, which is the closest area where there was a floristic survey. A very high percentage, then, of the trees of the region are present still on these farms. This has strong implications for the biodiversity that depends on trees. In this graph, I'm showing the correlation of the tree species richness with a variety of other components. And I'd like to just point out that the total number of bats and the forest bats, the total number of birds and the forest birds, as well as insectivorous birds, were all positively correlated with the number of species of trees. So having more trees in the landscape is building the basic structure to provide habitats for other organisms. Now, I don't want to leave you with the impression that all types of plantations are going to be rich in biodiversity. In fact, some are notoriously poor, including oil palm, which you've heard about oil palm from several people today. It's not that we can't do anything to improve oil palms, but as they exist now, oil palms are not good for biodiversity, and yet they're covering over 13 million hectares of the tropics, particularly in lowlands. And the establishment of oil palm plantations is replacing native forests, and especially some of these young secondary forests that are now in the short-lived secondary forest category. And this is particularly happening in Malaysia and Indonesia, where 80% of the world's palm oil is produced. These are some data actually from oil palm plantation research. On average, across a wide range of different taxa, only 15% of the species that were recorded in the nearby primary forests were found in the oil palm plantations. And the green bars here are just the forest species. So they don't do too well in oil palm. So now I'd like to turn to secondary regrowth, which is an area of my own research interest. And as you've been hearing, secondary forests are increasing in extent and in importance as forest habitats throughout the tropics. And even though some of the numbers that you've heard earlier today might not lead you to think that they're so important, I'd like to point out that there are 42 tropical countries throughout the world that have a higher area of degraded and secondary forest than they do of mature or old-growth forest. So for many parts of the tropics, these secondary forests and also disturbed or logged forests are most of what they have. So that's basically it as far as the prime habitats for biodiversity. Also, that because of the highly dynamic patterns of land use, secondary forests are highly vulnerable to conversion to agriculture. And even though I wouldn't advocate protecting a secondary forest over protecting a mature forest, I do feel strongly that conservation has to include all forest cover. And especially in areas where there isn't mature forest, protecting the secondary forest is just as important. One study that has looked at the biodiversity in secondary forests was recently conducted in Brazil in an area called Jari. And this study is one of the few that has looked at multiple different taxonomic groups within the same area. And this is the direction we need to go in. This study showed that in 14 to 19-year-old secondary forests, anywhere from 35 to 95% of old-growth forest species were found. It ranges a lot. The more easily movable flying species, like bees and flies and butterflies and bats, are much more likely to reach secondary growth and live there. Whereas trees and some of the less mobile lizards, for example, are not as likely to colonize the secondary forest. But keep in mind, these forests are less than 20 years old. They haven't had a huge amount of time to accumulate species. Also, the study looked at biodiversity in eucalyptus plantations in the same region. And except for grasshoppers, all of these taxonomic groups showed a better representation, higher representation of mature forest species in the secondary forest than they did in the eucalyptus forest. In a recent study that I've conducted with some collaborators in Costa Rica, we wanted to take a larger scale landscape view, and we looked at the trees that are growing in secondary forest and in many, many different areas, and also we looked at many different areas of old growth forest to accumulate a very large area sampled. So these are trees above 10 centimeters growing in the forest. From the data set, we basically plotted each species here and plotted the number found in old growth versus the number found in second growth. And you have the impression here that there's a large number of species that are found in both types of forest. In fact, 59% of the old growth tree species were found as trees in the second growth forest. These second growth forests ranged in age from about less than 10 years old to about 40 years old, 45 years old. I'd also like to mention that we discovered a large number of species that are simply too rare to be able to tell with any kind of statistical model whether or not they are a mature forest species or a secondary forest species. And this is a problem with doing these kinds of biodiversity studies, even with a large sample. Most of those old growth specialists that I talked about are actually regenerating in secondary forests. So we also have data on seedlings and saplings. We looked at those species. And we found that of the 123 of those species that did not have trees in the secondary forest, 94 of them had seedlings or saplings. So that ended up with a picture of 90% of the old growth tree species being present in some size class within second growth. And I think that's a pretty promising picture for this region of Costa Rica. So one of the main messages I want to give you about secondary forests, though, is that these are works in progress, that these are forests that are under construction, and we can go there and we can sample and get information about them today, but that's not necessarily going to give us a picture of what might be there in the next 5 years, or 10 years, or 20 years, if that forest is still persistent. And a lot of that question depends on who's surrounding, what the kinds of landscapes surrounding that forest, and how connected is that forest, and what is the fauna like, the birds and the bats that are going to bring the new species. So there's many questions that we don't always know the answer to, but we can look at scenarios that are good scenarios and scenarios that are bad scenarios and get a bit better picture of what's going to happen. These are some data that we gathered from a variety of studies, and studies where they had several different ages of forests under study in one area. And we looked at the proportion of old growth species as a function of the age of the forest when it was sampled. And in all of these different groups, we have flying animals, non-flying animals, trees, herbs and lianas, and some seedling data. In all cases, we found that the number of forest species, the percentage of forest species increased with age. And this is the expected pattern in forest succession, that species are accumulating over time. Now, what we don't know is if we study a particular forest, do we see this same increase happening over time? Because we don't have the long-term studies yet to really assess that pattern. But there's a suggestion here that we should expect to see an increase over time. I'd just like to end my talk talking about what we can do about this and how we can use this information to design and manage the agricultural matrix and the component forest patches to try to do our best to ensure the long-term conservation of biodiversity in the tropics. And this is really a perspective on conservation that is forward-looking. I view these entire landscapes as under construction. First, I'd like to emphasize that modified landscapes cannot substitute in any way for intact forest reserves, that the types of strategies that we can do must complement existing conservation efforts in protected areas. And I'd like to think about the protected areas as the backbone of our conservation strategy and the modified landscape work as the rest of the skeleton, to really give this whole effort the body that it needs, the effort that it needs. Once we, the first step in this approach is really to identify and to prioritize landscape hotspots. These are areas of modified landscape where significant biodiversity has already been retained. So we have a lot of building blocks that we can work from. And here we'll have our best chance of recovering and protecting biodiversity. So within these areas, we should conserve remaining forested habitats, even though they're not pristine forest. And we should restore remnant native habitats and isolated trees within this matrix. And we can be engineers. We can be active in the construction process. We can use secondary forests and strategically decide where those forests should be. We can use agroforests to connect and expand remnant areas. And we can create, through these efforts, biological corridors, buffer zones, and stepping stones, and gradually reconstruct a landscape that will work for many species. Oops. And I envision this process to one of building an arc, but here we're building an arc out of the entire landscape and actually trying to build features into it. And we can restore the degraded, unproductive lands through reforestation, natural regeneration, and enrichment planting in many areas. And finally, but not least, we need to promote and conserve indigenous, traditional, and ecologically based agricultural, agroforestry, and forestry practices that we know are adequate for conserving many plants and animals that we want to retain in our landscape. Thank you.
All right, let's see if there are a couple quick questions for Robin, just in terms of clarifying the talk. Yes, sir?
I'd like to ask if the Kabruka system is actually regenerating itself, because my impression is that the Kabruka system is good for biodiversity as long as the original trees are still living, but they're constantly being cut out of the understory, so there's not going to be any hope for preservation in the Kabruka system.
Yes, the question is whether there is tree regeneration happening in the Kabruka system. In fact, there is a new effort to prevent some of that thinning from occurring. Obviously, you don't want to kill the cacao trees because the system is there to grow the cacao, but there are some experimental efforts, experimental studies of ways of allowing tree regeneration in the system. So I think there's a lot of potential to do that.
John?
Robin, it seems like your agroforestry systems or agriculture and secondary growth systems are kind of halfway between or along the spectrum of in situ conservation and ex situ conservation. We can think of botanical gardens as being the extreme, really. I was just back from China. They have 60% of the plant species of China now in ex situ conservation in their botanic gardens. Could you give us some perspective on how your system falls between those two extremes?
Well, I do think that we need to do a lot more engineering out in the natural landscape, and we're not used to thinking that way. We're used to thinking about conservation is keeping it as it is, but keeping it as it is isn't an option if we really want to save most of these species. So I think we need to take the knowledge we have on silviculture, on cultivation, on what species do well from botanical gardens, and use that. We need to do enrichment planting. We need to come up with new models for building essentially new ecosystems, or at least giving them a start. Mm-hmm.
Jim? Oh, yes.
I wondered about,
We're getting a mic. Right there.
you mentioned eucalypts. 50 years ago, I was in southern Turkey, which is almost a rainforest area, and there were eucalypt forests. There were virtually no birds in those forests, and yet the eucalypts were huge trees that they were using because they were rapid growth and because they were excellent for making crates. How can you discourage people from using exotic species in these wonderful forests of South America, for instance?
I think you can encourage farmers to use native species through incentives. I think that that's what it would take. You have to provide them with incentives and with training, and we need a lot more information on how to grow native species. And there are many native species that would do very well in this situation, but we need to encourage the research and then encourage the planting through incentives.
All right, thank you very much, Robin. We can come back to that point in the debate. Thank you. Okay, so we have one more talk before we take a coffee break and stretch our legs. The next speaker is Nigel Stork. He is the head of the Department of Resource Management and Geography at the University of Melbourne. Many of us have known Nigel over the years from his work largely in insect biodiversity, and he used to be at the Natural History Museum in London for many years, and then was the CEO of what was known as the Rainforest CRC in Northern Australia. So his talk today is about extinction proneness among different groups of organisms. Are we really losing 100 species a day? Are we? All right, Nigel.
Thank you, Christian. You better just help me get my... Well, g'day everyone, as they say. It's a great pleasure to be here, and I have to say I'm really delighted to be involved in this debate. I remember about 15 years ago when I started to give... my slide's on that one. Yeah, it's on that one, yeah. To give my thoughts on this, and I was told by one eminent scientist that I shouldn't be giving these kinds of comments because I was talking against conservation. And so I really relish this approach that Bill and Joe have taken of really having a full discussion about the issues that are involved here. I'd also like to say that, believe it or not, there are rainforests in Australia. And Australian rainforests suffer many of the same problems that they do around the world. We've just put together a book which is published by Wiley-Blackwell's, which I think is probably the most comprehensive book on looking at issues to do with Australian tropical rainforests. It's called Living in a Dynamic Tropical Forest Landscape. Okay. Okay, thanks very much. So the question that I posed here today is, are we really losing 100 species a day? And if not, why not? And I come from this with the perspective of being an insect biologist. And a few years ago, I was looking at a Time magazine article, which was a really great article. It was talking about primate conservation. And in the sort of byline at the top, it said, as far as we know, no primate became extinct during the 20th century. That's an impressive record since the world loses about 100 species a day. Now, I didn't know where that quote of 100 species a day had come from, so I thought I'd really take it up. When something's published like that in Time, it reaches a very wide audience, and people will take that sort of thing as gospel. So if you look back in time, and it was very interesting to be around at the beginning of this kind of debate and to see what was going on, the biodiversity crisis really was brought to prominence by a number of very key and eminent scientists who did some wonderful work. And to me, three major issues really brought that issue to prominence. One was the work of Norman Myers, who identified the massive tropical forest loss around the world. Quite extraordinary work from Norman. And then, secondly, a number of people who, Tom Lovejoy, who's here today, I think, and Paul Ehrlich, Peter Raven, and others, who basically said, well, look, if we are losing this area of forests, then if we use that species-area relationship, which you've heard about today, then we're potentially losing a very large number of species. Now, added to that, until about the early 1980s, we thought we were probably around a couple of million species on Earth. And then a guy called Terry Irwin, who's from the Natural History Museum in here, was working in tropical forests in Panama and Brazil, and was using insecticides to knock insects out of trees. Discovered a very large numbers of species in the trees. And then he was asked by someone, well, if there are so many species in the trees, just how many species of insects are there in the world? And he set a calculation together where he said, well, if there's this number of species on this particular tree, and if we say 13% of those are specific to that tree, there are 50,000 tree species in the world, you multiply that up, and then if you add the things that are not only found in the canopy but are found on the ground, then you end up with 30 million species of insects on Earth. So with this forest loss that people were talking about, people suddenly thought, well, we're going to be losing millions and millions of species. And this is one of the quotes, typical quote from that time. Earth's biodiversity is being overtaken by a mass extinction which, if allowed to proceed unchecked, could well eliminate between 1/4 and 1/2 of all species. That was by Norman Myers. And look, here is a table that I and others put together at the time. I don't suppose you can read it all, but the first column is really the estimate of the sort of loss that people were talking about. The second one was in terms of percentage global loss per decade. And then the third column is a method of estimation. Just a second. I'm suffering from dehydration and jet lag. Now, if we actually, some of these estimates, we're talking about 30%, up to 30% loss of species per decade. And so this is 25 to 30 years ago. Well, if they were right, we should have seen the loss of at least half of all species on Earth. And in fact, we haven't seen that. And there are reasons for that, some of which have been discussed earlier on so far. But when you think about it, to a nearest approximation, all species on Earth are insects. There are millions of them. And of course, this is the sort of thing that you, a non-entomologist would think of as an insect, these beautiful, large, glossy things. This is a lovely drawer from the Natural History Museum in London, and it's all the big, showy things. But in practice, most of them are like this. Now, you can see the pin heads on those pins, and then you see going down the pin, there's a little white card, and stuck, glued on the end, very badly glued by me, are some little tiny beetles. This happens to be Staphylinid species number 57. Where's it from? From Australia. About 25 years ago, I was working with Terry Irwin, but I was working in Borneo, he was working in Panama. I was also using canopy fogging like this. And to give you an idea of just how many species of insects there are, I was using this fogging technique and fogging some large trees in Borneo, putting plastic sheets on the ground. I fogged 10 trees, and I had 20 square meters of plastic sheet under each tree. We fogged the tree, the insect rain would come down, you collect it up with some brushes, and you put them in a pot. Well, I was very disappointed because from those 10 trees at 200 square meters of plastic sheeting, I probably had about half a bottle of insects, that's all. What a waste of time going all there. Anyway, I took them back to the museum in London, and my colleagues and I then sorted the 25,000 insects that were in that bottle to 5,000 species. Some of those trees, some of those plastic sheets, there were over 1,400 species on a single sheet. So don't get the wrong, people have the wrong impression about insects. And most organisms are very small. So this is a pie chart. It's really from about 20 years ago, but it hasn't changed very much in terms of the proportions that we've actually described of species. You'll see that over a half, the bottom green area are the insects, okay? About a quarter of all described species on Earth are beetles, and you can guess which group I work on. So most organisms, therefore, are insects. The vertebrates here represent about 2.7% of those described species. Now, if Terry Irwin was right, of course, then the vertebrates would only be less than sort of 0.1% of all the organisms. Then we have things like fungi as well, and again, we don't know how many species there are of those. Some suggest perhaps up to 1 million species. We really don't know. The other thing about these organisms is that they play extraordinary vital roles in the way that our ecosystems function. And I'd give you an example from Australia as to how important these things are. You've probably seen these big hats that people wear with corks hanging down. You can buy them in shops in Australia. Well, people needed those 30, 40 years ago because the landscape was getting covered by cow pats, by dung, cow dung. Because the cattle are not native to Australia, there were no native organisms to break down cow dung. And thousands and thousands of hectares of land were getting covered in cow dung, which instead of breaking down in 3 months as it does here, it takes 7 years in Australia. and then there were lots of flies. So if we don't have these kinds of organisms, then we don't get the natural processes occurring. I just throw this in for particularly the people who might know a little bit more about this, but one of the problems with such estimates is someone saying, well, I think there's 30 million species on Earth, and other people saying 100 million, is you don't know how much certainty there is to those kinds of estimates. And this is some work that a number of us are working on at the moment, where we're trying to provide some sort of better certainty on those estimates. And we put a lot of data into this, into a mathematical model. And what this chart is at the top, I've done one for beetles at the top, another one for butterflies and moths, is the probability of the number of species on Earth and a number of species of these organisms on Earth. Where am I here? Not seem to work. So down. So this is the number of tropical arthropod species, 30 million up here. You can see a very, very low probability of that being the case. And the likelihood is that we are talking somewhere around 3 to 5 million species of insects on Earth. The other little chart that I've done here is to show whereabouts in the calculation is the greatest level of uncertainty. So we're just about to publish that work in the next few months. So I did say in my abstract that I'd talk about what traits make species more extinction prone. To some extent this is pretty well known for organisms, but it does vary from one group to another. In general, large body size makes species often more extinction prone, particularly ones with small ranges. And when they're restricted ranges, in other words, they're on the top of a mountain or they're on an island, they're even more likely to be extinction prone. Things that have low fecundity, in other words, they produce very few young and they're very slow to produce young, are also more prone. Things that are of a higher trophic level, in other words, things at the top of the predator chain, at the top of the food chain, are more likely, or actually are dependent on another organism, are also likely to be more extinction prone. And then those things that have a very low physiological or behavioral adaptability are also very extinction prone. So now I want to move on to extinctions then over geological time, just to give you a bit of a framework of what we know about the past. And I'm not a specialist in this area. I mean, there are people who work in this museum who probably know far more than I would know about this. But you'll see on this bottom graph here that at the left-hand side is the current period here, where we are now, and on the right is 540 million years ago. And you can see that over the period of time, the numbers of organisms, different kinds of organisms on Earth, is probably higher now than it ever has been at any other time. But we know that there's been these mass extinction events which have occurred in the marine environment when there's been massive crashes of those organisms. And we know that because these things have been very well fossilized, and there were sudden crashes in the number of those things. We know less about things where there's a low ability to preserve them as fossils. But that's a bit of a background. And it's been estimated that at least 96% of extinctions have occurred outside those mass extinction events. Often people think, oh, those mass extinction events wiped out most of biodiversity on Earth. But in practice, I think that 96% is probably an underestimate. And there's probably been a lot more extinctions that we just don't know about. Another phenomenon which is interesting is that when you, this is some data here collected by a range of people, but different kinds of organisms appear to have different lifespans as species on Earth. And if you look at the bottom, the mammals on average have a 1 to 2 million million years lifespan, compared to the invertebrates, which seem to have a much longer lifespan. Now, to me, I have to say this data I think is fairly flaky, but I think there probably needs to be more work done on that for it to be convincing. So I want to talk now a little bit more about the present, and that is that, and about global extinctions, and well, certainly in the last few hundred thousand years, and certainly up maybe in the last 2 to 3 million years since the advent of hominids. And during that period, we've seen half the world's megafauna, these are species of larger than 45 kilos, have gone extinct, particularly in Australia, Eurasia, Americas, and Madagascar. Also, over the last 1,000 years, there's been massive loss of these wingless birds, the ratites, and particularly on the Pacific and other oceanic islands. And those were really occurred when man first moved onto those islands, possibly 750 to 1,000 years ago. When you look at something like the amphibians in the last 20, 30 years, there's been a very large loss of amphibian species, but this is largely due to disease, particularly chytrid fungus and other kinds of diseases as well. And there's some implications that some of these species are also being lost through climate change. But overall, about 300 species of vertebrates are recorded as globally extinct in the last century, 0.4% of vertebrates. And this equates to about 50 extinctions per million species years, compared to what we think of the background rate of 1 extinction per million species years. So if you look at the extinctions of birds, and this is from some data by Groombridge, you'll see that most of these extinctions have actually taken place on the islands. This is actually an underestimate because it doesn't have a lot of those ratite birds included in there. Some of those bars should be much higher than they are. And in fact, birds have been particularly well studied. And as I said, if there's a background rate of 1 species extinction per million species year, as we think, over the geological past, Stuart Pym and others have looked at the birds, and since 1600, probably about 1.3% of birds have gone extinct, and that's equivalent to 26 extinctions per million species years. But he thinks, and he and his colleagues think, that there are a number of factors which probably have increased that rate, and therefore if it's corrected for those factors, it probably is up to around about 100 extinctions per million species years. And they think with climate change and other major threats that we're actually looking at extinction rate by the end of the 21st century of 1,000 extinctions per million species years. But they did recognize in this paper that birds may well not be good predictors for other organisms. And I think that's one of the key points that I really want to make. We can't be certain that what we know about some of these very well-known groups can be transferred to others. Similarly, if you look at analysis of the threats to birds and mammals, and this is some data here for mammals in the dark histogram bars, and the grey one is for birds, and this is for Australasia and the Americas, we see that habitat destruction, hunting, and introduced species are the major causes of the decline of these species. So let's move then to the insects. And this is a recent phylogeny for the beetles. This is done by a group of colleagues at the Natural History Museum and elsewhere in London. And this shows the massive diversification of the insects of the beetles in the last 250 million years. And I haven't got it here, so I can't leave it. But this extraordinary diversification, just to give you an idea of how diverse they are, there's probably 150 families of beetles that we recognize, and quite possibly we could be looking at 1 to 2 million species of beetles. In this museum, I guess there will probably be about 10 taxonomists who will tackle a family each in terms of the taxonomy of those groups. So for the other 40 families, there aren't experts in those particular families. These are very diverse and very complex groups. But they appear to show very high survival rates of those lineages. And this is, I think, very typical of insects in general. And these red arrow bars here show when the last 3 mass extinction events, which admittedly were marine events, when they took place. And there doesn't seem to be a major hiccup in the evolution of the beetles at those particular periods in time. So what's happened? What about global extinctions of species? Well, we have far, far less data on the extinction of insects, and this is a similar chart here for the extinctions. It was 66 species, I think it's now 65. This largest species, which is the Lord Howe Island stick insect, which was thought to have gone extinct off the coast of Australia, has since been rediscovered in the last half-dozen years. It's very difficult to actually determine when a species has gone extinct. We know very, very much less about the insects. But again, if you start to look at the threats to those, and I've actually here resorted to looking at the British beetles, British insects, since they're so well known. And here I put down just 3 of those, just 3 families of beetles and what we know about the threats to them. And it doesn't really matter particularly that you can't read what the actual individual threats are, but if you look to see, for each of those 3 families, there's a different set of suite of threats that are causing the decline of some of those species in the UK. And I could put up another 10 or 15 families, and they'd each have a different suite of threats to them, which means that you can't necessarily just take any one of these families and study those and think you're going to be summarizing what's happened to the insects in British Isles. Now, about 15 years ago, some scientists thought that they could work out just about the decline of species and extinction rates from looking at how our records of species and their threat was changing over a period of time. And I won't go into the details of this, but basically they found that there were major differences between different families in the relative rates of extinction for those particular families. So that the palms, they thought 50% of the palm species could go extinct in the next 70 years. For birds, 50% in the next 350 years. And mammals, 50% in 250 years. Now, they obviously couldn't do anything about the insects because they don't have any data for those kinds of things. Just not enough information. But again, what I did was to look at the British information, and we know these insects and other organisms extremely well in the UK. And we found that in general, that there was something like a 7 times greater chance of a mammal or bird to go extinct in the UK than an insect or a spider or a mollusk. And I'm not going to go into details there, but so what we did was to see if we can back test this to see if this is probably true or not. So of 1,300 species of British insects, in other words, 0.7% of those have not been seen since 1900. This relative extinction rate of 7.1, will predict that 11 bird species should have disappeared from the British Islands. And in fact, that's exactly what's happened. 11 species have gone. So what does that really mean for global extinction rate, insect extinction rates? Well, we know that 1% of birds and mammals are extinct, at least 1% is extinct since 1600. And that suggests if we use this 7.1 ratio for the insects, then only 0.14% of the insect species should have gone extinct as well. If we assume this is 8 million, this is just a figure I plucked out of the air, then approximately 11 to 24,000 species have gone extinct since the year 1600. And even if all of those have been lost in the last 50 years, then that's equivalent to 5 to 10 a week, not 100 a day. And so I have to question this business of 100 species a day going extinct. I'll come back to that in a minute. Smith and others, I showed you before, suggested that there's going to be something like a 12 to 55 increase in the extinction rates for birds and mammals over the next 300 years. Well, that relative extinction rate would suggest something like 1.7 to 7.7% extinctions over the next 300 years. And that's equivalent to 100 to 500,000 insect species. Now, again, this is very speculative, but it just shows that there are some major differences in people's approaches. Another thing I wanted to mention then is the business about co-extinction. And a few years ago, I was working with a colleague of mine who's worked on lice. And he mentioned about these two species of lice that had disappeared when the passenger pigeon, last passenger pigeon, died. In fact, they've got the names Columbicola extincta is one of them. So it was described after the passenger pigeon had gone extinct. And that put in train some thought that, you know, with a lot of these species, there must be those which are very host specific to birds and mammals which are going extinct or have gone extinct, or even to plants that are highly threatened or extinct as well. And some people have actually worked out then the sort of rates of co-extinctions are likely to occur. They're not actually as high as what one might expect, and that's largely because there's much less host specificity, particularly for insects on plants, for example, than we might have imagined 20, 30 years ago. So I'm now picking back up on some of the arguments that other people have made here. The species extinctions due to loss of tropical forests appear to be much less than people had originally thought 20 to 30 years ago. And I think part of that was because when they were doing those calculations, they basically assumed that these areas were being cleared and that it ignored the regeneration. It also assumed that the non-vertebrates, the insects and so on, the vertebrates, the fungi and so on, were as equally threatened and equally vulnerable as the vertebrates, and that's not so certain. More important, there appears to be this thing called a relaxation period when you do have these contractions in forest areas, but you don't get immediately the loss of species that you might have expected to occur. And what we don't know very much about is just those relaxation periods and whether there are major differences for different kinds of organisms. And in that sense, is the forest regrowth that Robin was talking about and Greg, is that regrowth faster than some of those relaxation times? In other words, do we have some buffers for some of these species for them to be retained? Okay. Couple of minutes, okay. Finally, I'm just going to move on to a couple of things. This is some more information similar to the stuff that Robin was putting together, which is about different kinds of organisms and how they're affected by changes in tropical forests. Now, this was a massive experiment I and a number of others carried out in Cameroon in the early 90s. When I say massive, you're dealing with very large areas of forests that you're manipulating in different ways. It took many years to actually prepare, and many years to sample, and then many years to actually sort the species afterwards. What we were looking at is a range of different forest types, and then a range of different organisms to see what happened to them. And if I go back up here, that red arrow going down the side on the left shows the from the pristine forest then right down to the most affected forest, most cleared forest. And on these plots here, it's the same arrow there from the left-hand side, the near primary forest, right through to cleared forest on the side. What we found in these different groups of organisms is that when we tried to make correlations across them, we found that no single group was an indicator for another. There were very few correlations. Butterflies were not a good indicator for birds, and so on. And I think that's one of the major problems that we have at the moment. Typically, people use butterflies or dung beetles as indicators, as token insect groups, thinking that they're representing the insects. Well, they're the giants of the insect world. They're not typical at all. I'll put this slide in here because this is some work I recently done. Cyclone Larry, a Category 5 cyclone, hit Cairns, where I was living a couple of years ago, devastated the forest there. It was a very frightening experience. We had some before experiments on insect diversity there and afterwards, and a year after, the samples were very similar to the ones before. So the insects are very resilient indeed. So one of the things that I'm concerned about, and I think this is important for science, is that there really are few studies that demonstrate the validity of using a particular non-vertebrate taxa as an indicator or predictor for other groups. As I said, some of the groups are token ones that people tend to use. In general, there's been a lot of very poor experimental design, low-cost projects because the funding has not been so good, and therefore there's a difficulty in extrapolating those results into a global context. And we need to take more of a shopping basket approach. In other words, looking at a range of organisms. Got 2 more slides or 3 more slides, if I may. Okay. What I want to draw attention to is that one of the things that we haven't really considered very much here is, do some of these threats actually act together? Are they working synergistically? Or do they work in independence of each other? I'm not going to go into that into detail now, but the right-hand scenario here shows where we've got some of these things like climate change, habitat loss and harvesting acting synergistically to create more extinctions than we previously thought. So in summary, a lot of global extinction rates estimates, which we currently still use, are based on those species area relationships which we know don't appear to work. At least they don't appear to be working at the moment. The loss of that change of habitat doesn't automatically translate into species extinctions. Global extinctions are much rarer than widely thought. Currently, they're mostly confined to islands and a phenomenon of vertebrates. Extinction threats vary for different taxa, and some groups may be much less threatened than others, and co-extinctions are also probably rare. However, and Joe's going to talk about this a bit more, I think climate change will change all of that this century, and it'll certainly tip the scales in terms of massive extinctions in this century. Thank you.
All right, thank you, Nigel, for that provocative talk. We're out of time for questions now, so I'm going to suggest that we go ahead and take a break, and then when we come back to the debate, there may be other questions. So there is a coffee break ready in the Atrium Cafe, so if you want to go up the 2 doors, stretch your legs, and we'll come back in 15 minutes. Thank you.